If you just start to study topology and you want to have an informal conversation of some of the concepts, such as a fundamental group of a plane, a fundamental group of a sphere, of a torus, or like a wedge of two circles, then this video is for you.
So what right now we do, and we're going to talk more about this, you have topological spaces and you want to go and be able to tell if they're homomorphic or not. So far, what we used two invariants. The first invariant is dimension, and the second invariant is kind of property, is compactness for the space. So example, when Rn is homeomorphic to Rn.
They're going to be homeomorphic exactly when n equals to m.
Here you use the concept of just dimensional rule, but what about like R2 and S2, when S2 is a sphere? Are they homeomorphic or not? Yeah, they're not. Why not?
Because R2 is not a compact set, but S2 is a compact set.
But let's say you have other two spaces which are more complicated. The compactness will not work anymore. Sometimes compactness is really hard to compute. So what do? You want to need to come up with different invariants, different like objects of study.
For the next part, I define two different types of invariants that we can have either homology group or homotopic groups, and I start to talk about fundamental groups.
Yeah, so first of all, is going to be the equivalence classes. The elements are going to be equivalence classes of what?
The equivalence classes of fundamental group are going to be point-based with the origin at x0, the closed groups in the topological space X.
But then the question is, if I'm going to give you two loops in X, and how do you determine that gamma 2 belongs to the equivalence function of gamma 1? So this one is equivalent, as to say gamma 2 belongs to the equivalence class of gamma 1, or gamma 2 is equivalent to gamma 1.
So two paths are equivalent if they are homotopic to each other. Homotopic means that I can deform one path continuously without breaking into another path.
Let's just do some examples to see that you have an intuition how. The most basic one, what is the fundamental group of R2?
The fundamental group of R2 is trivial because for any base point that we're going to take and attach a closed loop to it, we always can shrink it back to that point.
What about a circle?
In the case of S1, whenever we're going to pick a base point and go around the circle once, we're going to come back to this base point. But as you can see, since we have a hole, we will not be able to shrink that path to a point. Since we can go clockwise or counterclockwise any number of times, that's why the fundamental group of S1 is integers.
And that integer value corresponds to what? Yeah, how many times you wrap around clockwise or counterclockwise? Okay, what about this one? S1 cross S1. So P1 of, it's kind of torus. Also, it's indicated by this, by T2 of T2. This one, integers cross integers, is because you have this loop here, which is possible for one integers, and you have kind of outside loop here. So this inner loop responsible for direction A, let's say, and this one is responsible for direction B. But more interesting one is like, what if you have S1 wedge S1? So we have P1 of S1 cross S1.
The fundamental group of S1 wedge S1 is going to be a free group of integers with itself. To understand why is that, we need to look at the tree which is generated by loop A on the left and by loop B on the right, but we're going to do it in the next video.